So in this video lesson we've got 4 things to do regarding the Arrhenius equation. First of which is first of all understanding what is the Arrhenius equation. Then we will look quantitatively at the effect of temperature on the rate constant. After that we'll do some calculations. For example, we'll be provided with some data and we'll be able to work out what the temperature of the particular reaction is, or we might have to work out what the activation of a particular reaction is. And then lastly, we're going to rearrange the Arrhenius equation and plot graphs with it so that we can find values such as temperature and activation energy in a graphical way. So that's the 4 things we're going to do. But first let's have a look at the actual Arrhenius equation. Here it is. K equals A e to the power of minus EA over RT. And let's go through each component of the Arrhenius equation, starting off with K, which is of course the rate constant. That's that. Now A here is the Arrhenius constant. Named after the man himself. And E is Euler's number, of course, from natural logs, and that, if I remember correctly, is 2.718, etc. From your maths, you'll know that. EA is the activation energy. And the interesting thing here about the activation energy is the units, and the units in the Arrhenius equation are joules per mole. Alright, normally when we're talking about activation energies we talk about kilojoules per mole, and so often in a question you'll be required to notice that and convert from one to the other. R is our gas constant from the ideal gas equation. And you might remember that's about 8.31 joules per Kelvin per mole. And temperature, T of course is temperature in Kelvin. So that's the various components of the Arrhenius equation. As it happens, you don't have to learn it off by heart. You will be given it on your data sheet to take in with you in your exams. Okay, here's an interesting question to consider. What happens to the rate constant, K, it's just rate constant K, when activation energy changes? Now you'll remember from last year that you've got, let's say you've got any old endothermic reaction and you've got a big activation energy. That's going to be a slower reaction than a reaction with a smaller activation energy. So intuitively you already know that, where that is enthalpy, and that's the reaction process. So what we're going to do now though is actually look at it quantitatively. So let's remind ourselves of the equation. Here it is, and what we're saying is activation energy, right, is going to change, and what effect will that have on K and therefore the reaction rate? Well, let's for example assume that the activation increases. Okay, so more energy is required before you can get the particles to react. Let's say the bonds to be broken are getting a bit stronger. So if that increases, then it's a minus number, so this whole term here that I'm circling now, when that increases, that term becomes more negative. And if that term becomes more negative, then given that this is a constant, A is a constant, then the right hand side is going to get smaller. Right, so as activation energy increases, then the right hand side, and therefore K is going to decrease. And if k decreases, that everything else being equal, that means the rate will decrease. So that's mathematically how we can relate activation energy to the rate constant. You already know intuitively from year 12 how those two are related. And the same applies in reverse. Yes, in reverse. If you were to actually decrease the activation energy, so as you would decrease the activation energy, then that term, let me switch colours now, that term there is going to become a less negative number, and so the right hand side becomes a bigger number, so the k becomes bigger. So let's say k is going to increase, and everything else being equal, that means the rate would increase, which intuitively you would know. So a similar question is, what happens to the rate constant when temperature changes? Okay, so intuitively again from last year, you know that when you increase the temperature, reaction rates increase. The particles have more energy and more collisions are successful, and so the rate increases. So mathematically, let's have a look at it now. Here's our equation, and let's say that as our temperature in Kelvin increases, we look at this term here. So as our T increases, this number is going to be a smaller negative number. It's going to get less negative, and if that exponent is less negative, then the whole right hand side becomes bigger than it was before, and so K would increase. And the corollary of that is that as the temperature decreases, right, this term, the exponent term, if T is getting smaller, then the exponent is getting bigger and becomes more negative, in which case the right hand side is getting smaller, and so K would decrease, and therefore rate would decrease, all else being equal. So that's mathematically, quantitatively, what happens to the rate constant when temperature changes. Okay, what we're going to do here is have a go at using the Arrhenius equation in this question here, and we have some dinitrogen pentoxide here, and it's going to decompose. So we're given the temperature, and we're given the rate constant, and we're given the Arrhenius constant as well. And what we need to do is calculate the activation energy, and in brackets here is R. So first of all, let's write down our equation. So if you remember, our Arrhenius equation gives us K, so K is the Arrhenius constant, and it's e to the power of minus the activation energy over RT. And what we want is the activation energy. That's what we've been asked for in the question. But the first thing you would do is you would take logs of it to simplify it, take natural logs of it. So natural log of both sides, so log K is going to be equal to the log, and in brackets we'll put a e to the minus activation energy over RT. We put that whole lot in brackets, which from your maths you know that you can separate out into log A plus log, natural log of e to the minus EA over RT. And taking a natural log of Euler's number e just leaves you with the exponent, so we can write that down. Everything else is the same, but taking a log of Euler's number leaves us with minus EA over RT. And hopefully you know that from maths. If not, then we'll have to help you with your maths. But let's remember that it's activation energy EA that we need, and so we need to get that out on its own. So why don't we multiply both sides by RT. Just doing a little swap first. So now we have EA on its own, and in fact all that's required now is to substitute in all the values. So A, we're given, where is it? Yeah, it's 4.79. Right, times 10 to the 13. Log K we're given, where's that? Yeah, rate constant 1.35 times 10 to the minus 4. And R we're given 8.31. And temperature we're given 308 Kelvin there as well. So if you plug everything in, and just having a quick look at, yeah, so all the units are okay to plug in. So then you would get EA coming out at, if you plug all those in, 103,429.54 units, being joules per mole. Alright, but normally we are required to describe activation energies in kilojoules per mole. So to three significant figures, that's 103 kilojoules per mole. QED. And here we've got the same reaction. So it's the decomposition of dinitrogen pentoxide, I seem to remember, and that's set up at a different temperature this time. So of course K changes because the temperature has changed, and in fact we are given the new value for K, so that's not a problem. And we're also given the Arrhenius equation, and it says that all other conditions remain the same, and what we have to calculate is the temperature at which this reaction occurs. So if we start off by writing down Arrhenius equation, rate constant equals our Arrhenius constant times e to the power of minus the activation energy over RT. So if we have a look at that, we know that we've actually got all of the information apart from what we're being asked for, which is the temperature. So the question is just an exercise in rearranging Arrhenius into a form that gives us temperature on the left hand side, after which we just plug in all our known bits of data, and out will pop our answer. So let's go ahead and do that. And first of all, we're going to change that into the log form of Arrhenius. So we're going to have log rate constant is going to be a log of our Arrhenius constant minus our activation energy over RT. Take it you can remember that little process of taking a natural log of Euler's number. They're just inverses of each other. So we're left with this. That's our log form of Arrhenius equation, and we want temperature. So we're going to rearrange to give us temperature on the left hand side. So first of all, why don't we just switch our term EA over RT onto the left hand side, so making it positive, and so then we're left with log A take log K on the other side. Multiplying both sides by T would leave us with EA over R equals T times log A take log K. And finally, dividing both sides by log a take log k will leave t on its own, and I'll just switch it over to the left hand side while I'm at it. So t is going to be EA divided by R times log A take log K. So let's substitute in our values. EA we worked out in the previous question, but remember it needs to be in joules per mole, so we're going to convert it back into joules per mole. So wasn't it 103,430, let's call it, divided by R, we were given R in the previous question, you'll remember that's 8.31, and then we're going to times that by log A. The Arrhenius equation constant is given us in the question, 6.22 times 10 to the 13, and then we're going to take our log of K, and again that's given us in the question, so that's 2.4 times 10 to the minus 3. Put that in your calculator and you come out with 329 Kelvin to 3 significant figures. QED. So now with this worked example, what we're going to do is we're going to see how we can use Arrhenius equation to plot graphs and therefore find valuable information, such as rate constants or temperatures of reactions. So here we have a data table for a reaction, right? And we're given various temperatures. We've got various temperatures here on the left hand side, and for each temperature we're given the rate constant K. We're given kindly 1 over temperature, and we're also given the log of K. So we're not required to work any of that out ourselves, but we're given the information that we need to plot a graph. Right now, so here's the thing about plotting graphs using Arrhenius. We use the log form. Right, so let's just remind ourselves what the log form of Arrhenius is. So we got log of the rate constant equals the log of Arrhenius constant minus EA over RT. And whenever you see a question about plotting graphs, then you might remember the equation for straight line. Alright, so you remember that from GCSE Maths, y equals mx plus c is the equation for any straight line. And you'll remember also that m is the gradient and c is the intercept on the y-axis. And so let's have a look at Arrhenius equation in log form here on the left, and see if we can put that into y equals mx plus c format. So if we let y be log k, and if we let x be 1 over temperature, and we plotted log k against 1 over t, then m would be, the gradient would be EA over R, and the intercept would be log of the Arrhenius constant. You see that? So y equals c plus mx, where that is m, and 1 over t is x. So it's worth spending a few seconds just looking at the log form of Arrhenius and translating that into y equals mx plus c format. Do that in your own time. What we're going to do is move on to actually plot this data. Here in the top right hand corner we've got the same data table and the same question superimposed on a bit of graph paper. I don't have a ruler, so my lines are going to be all wonky, but hopefully the message is clear. So as we said, we're going to plot log k. Y is our log k. Here's our log k. Okay, if we look at this data here, and you can see it goes from, the biggest number is minus 40, and it goes right down to minus 109. But we're often interested in the intercept of the y-axis, so why don't we choose a range between, let's say, 20 and minus 100 and minus 120. We'll have a range like that. So we're going to have our y-axis like this, where we'll put about minus 120 down here. Let's have, that will mean that our zero is about, let's put our zero about here, in which case we're going to have plus 20 about here, and so that's going to be 80, 60, 40, 20, all very rough, I'm sorry. Roughly like that. And then our axis will extend out here, and we're plotting, our x is going to be 1 over t, so this is x here, and you see x is going to go from, our smallest value is about 0.0025, but again we want it to start from 0, and it's going to go up to about 0.0067, so we're going to plot it to about 0.007. So here we want about 0.007, so that's going to be about 0.003, so that means that will be 0.001, 0.002, 4, 5, 6, 7. Very roughly, there it is. So then, why don't we plot our points? Let's change colour just for the fun of it, and plot the point for temperature 150. So temperature 150, 1 over T is 0.0067, so that's going to be about here on the x-axis, and our log K is minus 110, right? So let's put that there. It's very rough, I'm sorry. So our next point, for temperature equals 200, 1 over T is 0.005, so that's here, and our log K is minus 82, so we're going to put that point about there, and then the third point, 0.004, right, is minus 65, so that will be about there. What's the next point? 0.0033 is going to be about here, and that's minus 53, which is about here. Next point, 0.0029, which would be about there, and minus 46, which would be about there. And last point, 0.0025 is there, and it's going to be about minus 40, which is about there. Okay, so there we've plotted 1, 2, 3, 4, 5, 6 points, and that's the same number of data points as we have. And so actually, despite it being very rough, it's worked out at a reasonably straight line. All right, so I'm just going to extrapolate that straight line. Whoa, very wonky straight line. That's supposed to be a straight line. Anyway, there it is. So from the previous slide, you'll remember that the gradient is equivalent to minus activation energy over R. So if we worked out the gradient in the usual way, so this might be minus 78, and this delta x might be 0.0047. When you plot it properly, that's a couple of the numbers that you might get, and so the gradient comes out at about minus 16,596. So now we're just going to work through the algebra. So we've got minus EA is going to be minus 16,596 times R, which is 8.31, you remember? And so EA is going to work out at about 137,911. That's going to be joules per mole. And as usual, we're going to convert it into kilojoules, so it's about 137.9 kilojoules per mole. The question always also asks you to work out the Arrhenius constant, and there's two ways of doing that. First way is just to go back to the Arrhenius equation and take a particular set of data for a temperature. So why don't we pick 150 Kelvin, and so if we start with Arrhenius, K equals A e to the minus EA over RT, then rearranging that, A is going to be K divided by E to the EA over RT. And in fact we know all those now, so K at 150 is 4.59 times 10 to the minus 48 in this case. EA we've just worked out, 137.9 or 137,911 joules per mole. R, 8.31 we know, and temperature we've selected 150 Kelvin. So you just plug all those bits of data into your equation, and in this particular case A would come out at 5.1. Now what are the units? Units are for A seconds to the minus 1. And the thing to remember is the units of A are the same as the units for K. And the units of K are given in the question. I've just circled it in blue there. So there you have the units of A as well. And that's the question done. But while we're at it, why don't we just mention the other way of finding A from a plot such as this. You can find it from the intercept of the y-axis. So just looking at this position here, if you plotted it correctly, you could see that intercept was about 0.2. Not 0.2, 2 in fact. So from the previous slide, you remember that that means that log A equals 2, in which case A equals e to the power of 2, which you put into your calculators, and you come up with about 7.4 seconds to the minus 1, as usual. Alright, so that's the other way of finding A. So that's it virtually for this video lesson. Let's just make sure we've covered everything off that we intended to. Do we know what the Arrhenius equation is? Yeah, we've written it down quite a few times. I'm guessing you can remember that by now, so let's give ourselves a big tick for that. Then we wanted to explain the effect of temperature on the rate constant, and we had a look at the Arrhenius equation and saw what happened to the exponent as temperature changed, and what happens to the exponent then gives you an effect on the rate constant. So we did that. We used Arrhenius in calculations, And just now we've just rearranged Arrhenius, and we've plotted graphs with it to find out things like the Arrhenius constant and the activation energy from the intercept and the gradient. So there, we've done it. That's the sort of work you have to do for using the Arrhenius equation.